Did I hit record? I did. Okay. There we go. All right, everybody, let's get started. I thought it worth just having a rehash on the schedule and logistics. Like I was saying right before class, I don't think I've yet mentally adjusted to the fact that next Thursday and next Friday we're just not having class. I've been a professor for 10 years, never done this, so I don't believe it. I'll believe it when I see it. So, no, we're not having class on Friday, October 11th, and our exam is after the fall break. So you don't have to worry about any exams. We're not going to have any. Oh, it's a break. We got to have a bunch of exams and quizzes right before break. I imagine you have a professor or two who's doing that to you. I'm sorry. I'm not. So okay. I think we're rocking and rolling on grades. 3.5 still being graded, but everything else is still up to date. How did this last homework go? Did the trust make sense? Okay, I had a feeling. I think that you would be surprised that 3D, it might be a little long, but 3D is pretty straightforward. We actually have two 3D problems that we're going to do today. One of them, I'm going to skip some details on because after a while it just becomes chugging out cross products, and I don't think, once you get the point, you get the point. But the second problem I actually want to spend some time on because it sort of indirectly introduces a concept which we're going to look at later in the semester. Everybody get the code? Okay, so yeah, our second exam is Wednesday, October, or why did I put this? This is supposed to be October, not so. That's October. I'll fix it later. It's October 18th. We're not going to have an exam a month in the past. So, okay. You already had exam 2. You're like, we did well on it, right? Oh, let's move on. That was a joke, not a line. Okay. So what we're going to do is extend our discussion last time about equivalent systems into the third dimension. So the idea is, can we develop a new system of forces from a given system of forces that has static equivalency? In other words, do the sum of the forces in system 1 and the sum of the moments in system 1 equal the sum of the forces and moments in system 2? We're going to, again, right now, we are not setting these equal to 0 and solving for unknowns. We're going to start that on Friday. Okay? The goal in that aspect is to figure out what unknown forces are needed to attain equilibrium. We have a very particular name for those forces in statics. We call those reactions. Okay? Every action is equal and opposite reaction, right? So the idea, for example, the idea behind what we're going to start on Friday is if I have a beam with a bunch of loads on it, what are the forces that are required to keep the beam in equilibrium? Those are reaction forces. We're going to talk about that on Friday. Today what we're going to do is 3D land, and I've got two examples. One of them is, I'm going to blow through this one pretty quickly because I just want you to get sort of an idea of how it works. I actually want to spend a good bit more time on this one, okay? For two reasons. One, as you can tell, this is a very civil engineering themed problem, and civil engineering is objectively the best field of engineering that there is. Sorry for you biomedicals, you're just wrong. That was a joke, not a funny one. No, but in all seriousness, I really do like this problem because it will introduce a topic, it sort of indirectly introduces a topic we're going to discuss later in the class, which is the idea of a centroid, okay? And we'll get to that a little bit later. Let me go ahead and open up the notebook and talk a little bit about this problem here. So what we're going to do is replace the forces on the bracket with an equivalent force couple system at point A. So let me just sort of take stock of what's going on here on this problem. So with this problem, we have a bracket and we have a series of forces. We have a 1,000 Newton force here, a 700 Newton force here, 1,200 Newton force here at points B, C, and D. So I did that in the wrong order. So the 700 at B, the 1,000 at C, and then the 1,200 at D. For each of those three forces, we have a requirement to describe those in IJK notation. Now, we have done that all semester, right? That has been something we have done this entire time, right? What do? We get a distance vector, then turn it into a unit vector, then take that unit vector, multiply it by the magnitude to get a force vector, okay? That shouldn't be anything new, right? Or it really shouldn't be, right? We then need R vectors. So for example, R from A to B, R from A to C, R from A to D, for the purposes of computing cross products, right? So the first step in a problem like this is to just describe all your vectors, which I hope by now is like old hat at this point. Like we've done this enough at this point, right? So if I want to replace this with an equivalent force system, really all we need to do is sum the forces and sum the moments, okay? And again, that part should be pretty easy. So if we want to determine a resultant force vector, and these are in newtons, we have FB, which is 300I minus 600J plus 200K. We have FC, which is 707I plus 0J. I think I put minus 0J in the example. That doesn't matter. 707K. And then we have FD, which is 600I plus 1039J, and then plus 0K. If I want to define the resultant vector, that's pretty easy. If I have a series of forces, how do I find the resultant force vector? Just add them up, right? So the resultant force vector is just going to be adding all these up. So 300 and 600 is 900, 707, that's going to be 1607I. Plus, this is going to be 1039 minus 600, 439J. And then minus 507K. That's in newtons. That's my equivalent force vector. So again, once you describe them, it should be a pretty rote process, okay? Now, this is how I get the resultant force vector. How do I get the resultant moment vector? Well, if the resultant force vector is determined by summing the forces, the resultant moment vector is determined by summing the moments, right? And how do we sum the moments? We sum each of the cross products, right? That's what we do, right? So how are we going to do that? So pretty straightforward. So we're going to handle this as follows. So for example, for the moment from the force at B, all we're going to do is take that R vector and cross it with FB. And the R vector is just going to be 2B from point A because we're summing moments at A. So how are we going to do that? Well, here's that vector. There's that vector. just write it out and chug it out, right? So and we just evaluate it. Now, here's sort of the point I'm making here. Do we really need to go through the steps on this? I mean, if you want to, we can, but I've got to believe by now you all have done enough cross products that at this point, if I go from here to just the answer, which the answer ends up being 30I plus 0J minus 45K, and that's going to be in Newton meters, that you can sort of take my word for it that that's the answer. Is that fair? Okay, I'm hoping by now that that's doable. Okay? If that's the case, then we'll just keep on going and just do the same thing. So what do we do for the cross product of M and C, or of the force generated at C? We take the R vector, cross it with the F vector. Okay? And again, I hope that you just trust me on this. This ends up being 0I, 17.68J, and 0K. And then same thing with MD. That was C. And this one ends up being just 0I, 0J, and that. So just summing up these vectors, same idea. 30I, 17.68J, and this one's going to be something like 118.9K. Let me redo that. Bear with me. Okay. And that's basically it. I think my big point with this example is that if you describe the R vector, if you describe the F vector for each force, this is just kind of chugging it out. It might take a little while, but it shouldn't be conceptually difficult. Okay? Is everybody okay with that? Any questions? All right. If that's okay, I want to go ahead and move on to this next example. Again, I just want to do something civil engineering related. I'm being facetious when I say that. In all honesty, I really do like this example, but not for that reason. I like this one because it's a little easier to wrap your head around, but again, there's a really cool underlying concept in the background that I think is really valuable. Okay. All right, we have a square foundation in a building, okay? And so that square foundation mat supports 4 columns as shown. Often architects will lay out structures such that the columns don't occur at nice even grid patterns, because nice even grids make the engineer's life easy, but it tends to make the building kind of boring. You know, at some point, you know, you want the building to have some curves and have some flavor. And so, you know, you can have odd column patterns. This is not outside the realm of possibility. Okay, so we have a series of columns that are supplying load to the ground, and so the idea is to determine the location of the resultant. In other words, if I were to collapse those into a single load with a magnitude, where would I place that load to generate an equivalent system? Make sense? All right, so I've got 4 vectors. What I'm going to do is I'm going to replace it with 1 vector. Okay, now, one of the reasons that I like this problem is because the construction of the vectors is pretty easy. And so chugging out the math, if we wanted to do it by hand, would be very doable. Okay, let's go through this. Okay, now what I'm going to do for this problem is I'm going to take moments right here at point O. There is a specific reason I'm going to do this, and this will become clear as I do the math here in a bit. But one of the things that's kind of interesting about this calculation is that independent of where you choose to take moments, everyone, if you do the problem correctly, will locate the resultant at the same place. Okay? It'll be at the same place. Like, for example, if the resultant is here, everybody will get the same coordinate. So, but there's a reason I'm taking moments there. Okay? All right. Well, if you want a simple answer, it's because it's the origin. So I'm just taking moments at the origin. Okay. Let's put some structure here on this problem. So so that we're all speaking the same language. Let's number our forces. So we'll say 1, 2, 3, 4. Okay, so I'm just sort of doing a ring around the foundation mat. Okay. So actually, let me write like this. So let's write our force vectors and our R vectors. Let's do this. And maybe what might be a good idea is to do this in a table. I'm an engineer. I like tables. Okay. So let's write our forces out maybe first. So we sort of did this last time. We'll put a sum down here. Let's do our force vectors first. And I'm doing the force vectors first because I think they're the easiest. Okay. Help me out. I've got 40 kips, 8 kips, 12 kips, 20 kips. Along which direction are all of these forces acting? Like x-axis, y-axis, z-axis, what axis? The y-axis, but you said something else. What'd you say? Negative y. They're acting along the y-axis, but they're all acting down, right? So for example, F1 has a magnitude of 40 kips, and it's pointing down in the y direction. So if I were to describe F1 as a vector, how would I describe it? Negative 40j. So if this is negative 40j, what's this one? This one's going to be negative 12j, right? This one's going to be negative 8j. This one's going to be negative 20j. Does that make sense? They're all going to be just j vectors. And then if we wanted down here, we could go ahead and do this now. What's 40 plus 12 plus 8 plus 20? 12 and 8 is 20, 20, 20, 40, 80. So negative 80j. Okay. So far, so good? All right, so let's see. Now let's do the R vectors. Okay, this first one's kind of interesting. Okay. So the R vector, let's look at point 1. Okay. So we're taking moments at the origin. How far is it from the origin to the line of action of force 1? Trick question. Nothing, right? There is no distance. So what is the vector? It's just 0. Like 0i plus 0j plus 0k. So by the way, what is R cross F going to be for force 1? 0, right? Because what it's going to be is it's going to be I, j, k, and it's going to be 0, 0, 0, 0, 0, negative 40, right? So it doesn't matter which way you split it up. You're always going to have zeros, so that's how it's going to work out. Does that make sense? Okay, let's look at force 2. Okay, so from point O, from the origin, to point C, how far do I go in the x-axis?
10 feet.
How far do I go on the y-axis?
0.
How far do I go on the z-axis?
0.
So this is going to be positive 10i, right? Okay. So tell me what the vector is going to be for force 3.
0.
Say it again.
Is it 10I, 0J, 5K?
There you go. 10i, 0j, 5k. So we'll just call it 10i, 5k, just for shorthand. And so what's this one going to be? 4i plus 10k. Okay. Okay. So now what we'll do is we'll do some R cross F for each one of these. Okay. So let's see if we can do this quickly. Okay, so this one, that one's going to be 0. We don't need to worry about that. Okay. So let's see if we can do the next one. Okay. So this one's going to be negative 12. Okay. And this one's going to be 10. Okay. All right. So let's see what this is going to be. So it's going to be I, and then this minus j, and then plus k. It's going to be that, right? Did I do that right? So what's going to happen here? 0 and 0, nothing, right? This one's going to be minus 120, right? 0, but that's negative, so it's going to be plus 120j. And this one, 0 and 0. So did I do that right?
Is the 12 supposed to be with the J?
Yes, it is. This is why I have seconds. Yes, so this is negative 12. So that means this goes here. That goes there. So you're right. This is negative 120K. This is why I have seconds. Thank you. So negative 120K. So far, so good? All right, so let's see about this next one. Let's see if I can do this one right this time. So I, J, K. All right, so the R is 1005. The J is 0 minus 80. Did I get that right this time? Did I get this right? Okay. So 0 minus 850. Let's see, minus J 10 0 0 or 10 5 0 0. And then this is 10 0 0 negative 8. Did I do that right? So that's negative 40, but it's subtracted, so 40I, 0 0, and then negative 80K. That do good? So this is going to be 40I minus 80K. And then if you'll trust me, I've got the answer for this one. I've got 200I minus 80K.
Why is it positive 40?
Because, okay, all right, because, okay, so it's this times this, minus this times this, and that's negative, so it's two negatives. That's a good question. So that's an easy thing to, I mean, I put stuff in the wrong column, so don't feel bad. All right, everybody good? So now what I'll do is I'll sum up these, so, and I'll get, so on the I terms, I got 240. And then on the K terms, I've got, what is that, 280? Negative?
Yeah.
Okay. So therefore, my system 2, I guess we'll call it, is this. In other words, if we consider point 0 or the origin, I can replace the 4 forces with these 2 vectors and I have static equivalency. But that's not really what the problem asked. What the problem asked is, where would I place R to generate the same moment? Okay? Everybody make sense? Make sense? Okay. All right, so let's answer that question. All right. Is everybody with me so far? Do I need to stay here for a second? Is everybody caught up on the calcs? Okay, all right. Okay. Please do not make fun of my horrible artistic skills. I will do my best. Okay. So here's the plate, the foundation, okay? And just to label the axes the way that they're labeled on the problem, this is the x-axis, this is the y-axis, and that's the z-axis, okay? And so what we're going to do is, remember there was like a load here, a load here, a load here, a load here. We were replacing it with a single load, right? A single load, okay? And that single load is going to be, who knows? I don't know. Let's call it right here. Now, what's the magnitude of that force, by the way?
80 kip.
80 kips, right? Okay. My question is, where do I place this? Okay. So I'm basically trying, in this case, to define R. Okay. Now R is going to be, if I were to write it, I don't know, symbolically, it's going to be that. Okay. Why am I saying it's that? Because I'm saying this dimension here and this dimension here are what I'm interested in. And we'll call this dimension RZ, and we'll call this dimension RX. In other words, how far along do we go along the x-axis? How far do we go along the y? Or along the z. The y direction doesn't matter because it's going along the line of action of y. So all we need to figure out is where do we place it in terms of x and z on the foundation. And then keep in mind our r vector, our resultant, was that. Now remind me, what did we get as m cross r? We got, what was it, 240i. $280J, is that what we got? Okay. So, maybe what we ought to do is take the cross product of these two vectors and see what we get. So what happens if we do this? So we get, it's dancing around on me. Let's evaluate this out. Let's see what we get. So we're going to get I times 0 minus 80 RZ and 0 minus J. We're going to get RX, RZ, 0, 0, plus K. And then we're going to get RX, 0, 0, minus 80. Fair point? What's going to happen on the J term, by the way? Kind of convenient that there's, this is a typo because nobody caught me on that. That was supposed to be a K. Nobody caught me on that. I'm the one who made a mistake. I can't get too upset. No, but it's kind of convenient that there's no J term here and there's no J term here. It's kind of funny how that worked out. So what are we going to get for I? So we're going to get 0 minus a negative 80 RZ. So that's 80 RZ. and then that's going to be times I. Then the j term is going to be 0. What about the k term? Negative 80rx minus 0. So we've got that, right? So I propose that R cross R is, we'll call it 80RZI minus 80RZK. And what was the moment vector? It was 240I minus 280K. So what does that tell me? Yep, sorry, yes.
Would, on the negative 80, would that be RX or RC?
Hold on, where?
In your RXR?
In your
Oh, this is RX, yes. Whoops. Talk about this one. Like that? Whoopsie. I know I'm only allowed 7 mistakes per semester. I've racked up a few of them today. I only had 1 cup of coffee though, maybe that's the problem. Okay, so if this is R cross R and this is my resultant moment, what can you tell me about like the terms? What can you tell me? What does 80RZ have to equal? And 80RX has got to equal 280, right? So that's 3.5. So therefore, Rx is 3.5 feet. RZ is 3 feet. So in other words, if here's my foundation and I have an 80 kip load and I put it such that it's 3.5 feet along the x-axis, 3 feet along the y or along the z, then it has the same static equivalence as all those other 4. Make sense? Now here's the interesting part, okay? Note the coordinates I'll call it 3.503, if you want to do that, are called the centroid of the load group. We are going to have a lot of fun later computing the location of centroids. I'll tell you that of all the topics that you learn in Engineering 213, being able to locate the centroid is among one of the easiest topics that we learn, but it is also one of the most important. Okay? Yes?
So in like a, if you were analyzing that like footing or that foundation there, what would you use this for?
That's a good question. So locating, so if we're fast forwarding into foundation design land, locating where the resultant is as an engineer would help you determine both the capacity of the foundation, but then other things like the stability of the foundation. Is it going to slide? Is it going to overturn? What have you? So the same thing is necessary for both foundations as well as retaining walls. So that's your short answer. Longer answer, CE 425. So Dr. Knott teaches that. Does a fantastic job. So, yes?
What happened with the negative on the RX?
What do you mean? Like, why is this negative?
No, like,
Oh, well, I just said, so if negative 80 Rx equals negative 280, then positive.
okay.
I was just being lazy. But, I mean, it was mathematically equivalent. Notice, well, here's something else. Would it have made sense if our answers were negative? No, because that would have meant they were off the slab, right? They were off the foundation mats, and the answers had to be positive. It also wouldn't have made sense if R cross R had a J term, because this didn't have a J term, right? It wouldn't have made sense. So that's why I almost like this problem more than the other one. Like, it's easier, but there's a lot more you can glean from it. So, but when we start getting into centroids, you'll see what I mean. Really, if we could actually have located the centroid of this load group in a much easier fashion. I'll sort of give you a quick, a peek behind the curtain on how you would do that. How many of you are comfortable with computing a weighted average? You ever done a weighted average before? So watch this. So I'll show you a little peek behind the curtain. And this is really only like a centroid idea. So 1, 2, 3, 4. Okay. So this was 40, 12, 8, 20. So we'll call this the force. What were the x terms in these vectors? So this was 0, 10, 10, 4. Did I get that right? Right, so this is this x term, x term, x term, x term, right? So here's how we compute a weighted average. Okay, let's take x times f. Okay, so 40 times 0 is 0. This times this is 120. This times this is 80. This times this is 80. That plus that plus that is 280. That plus that plus that plus that is 80. So the weighted average is the sum. You do that in statistics, right? And so it would be 280 over 80, or 3.5, right? And so you can do the same thing with the coordinates in the other direction, and you get a value of 3. What we just did right here, this is a centroid calculation. We're going to do this after exam 2. So it's the same idea. How about trip over my bookcase or my book bag? All right, let's take a step back. How are we doing on this? Does this make sense? Okay, so this is it for our rigid body systems topic, okay? So the goal in this module, this sort of third module in the class, this rigid body systems module, was to be able to take, there's really twofold. The first was understanding what moments are. But then the second, the real big goal was this, taking a system of forces and resolving them into an equivalent system, which is the sum of forces and the sum of moments. What we're going to start on Friday is rigid body equilibrium, how to take those sums of forces and sums of moments, set them equal to 0, and solve for unknown reactions to keep the system in equilibrium. And that is the beginning of analysis. And I don't care whether you're a civil engineer, mechanical engineer, biomedical engineer, being able to analyze structural systems, be they bridges or buildings or cars and airplanes or, whatever you biomedicals do. I'm being facetious, but not really. But any system that is subjected to forces, being able to analyze that system by determining the forces that keep the system in equilibrium, the resulting stresses inside the system, designing the systems to resist those stresses, it all starts here, okay? This is a really critical point in Engineering 213. I'm going to pull up the code one more time. I will see you all on Friday.